Okay, so here is mainly AP Stat notes on Chapter 7 from the book. Just trying to quickly summarize everything. We hit on a touch of examples. I kind of went through everything, but wanted to make sure that we kind of hit on each individual section here a little bit as well if you needed some extra help. So in Chapter 7, we were mainly focusing in on scatter plots and their correlation, right? Looking at the scatter plots, right? And I'll hit on these a little faster than normal as well, so if I'm moving too fast, remember to pause these videos. But a scatter plots may be the most common and most effective display of data that we get. And in the scatter plot, you can see patterns, trends, relationships, even the occasional extraordinary value, which we have those outliers that are sitting way out there that we talked about. And scatter plots are the best way to start observing the relationships and the ideal way to picture associations between quantitative values, meaning quantitative, quantities. So when we're talking about numbers, relationships between two numbers, it might be the best way that we have with two different value sets. And Unit 1, we're looking at one value set, right? So looking at scatter plots, we usually can look to see the direction that they're going, whether it's up or down, the form they're taking. Is it more like a straight line? Is it look it's curving a little more? The strength of it, like are they tightly close together in a straight line? And is there anything unusual that happens with the data? So you could have direction, a pattern that runs from the upper left to the lower right would be a negative direction. A trend running the other way from this way up would be a positive direction. Learned about this stuff basically in Algebra 1 when you're talking about slopes, right? So looking at a scatter plot, can the NOAA predict where a hurricane will go? So here's the data, right? And when we were looking at data before, it seems like a trend is going down, right? But I do have what appears to be an outlier out here, all right? And for the most part, they do appear to be going down. Some of these are also kind of random. So you would want to sit there and say, well, I feel like I could predict it looks like it's going down, right? So the figure shows a negative direction between the year 1970, right, and the predicted errors made by the NOAA. As the years have passed, the predictions have improved, right? So errors have decreased. So we could have had some errors here and everywhere before, but as technology worked its way down, maybe that's why those errors didn't exist anymore, right? So if I looked at this trend, right, again, looks kind of like it's trending down as well. The example in this text shows a negative association between the pressure, central pressure, and the maximum wind speed. So it looks like that we have some of this as well. And we don't know why some of these outliers might exist, but as the central pressure tends to increase, the wind also seems to decrease, is what's happening over time. Just looking at ways of reading the data. So we have some forms, right? If there is a straight line or linear relationship, it would appear as a cloud or swarm of points stretched out in a generally consistent straight line. That seems like it should be linear, right? It seems like a nice little pattern. They're all kind of working their way down, right? But look at this. If the relationship isn't straight, but curves a little gently even, right? While still increasing or decreasing steadily, something like this maybe, right? Looking at a pattern like that. It could be straight, but it looks like there's a pattern of even curving to me, right? We can often find ways to make it more nearly straight, right? And we talked about that in towards the end of our big overview videos. If the relationship curves sharply, right, like that, the methods of this book cannot really help us yet. Now, I went over some strategies that can help us if we end up having some curves, but the examples I showed you, we weren't really talking about anything that curves sharply, right? So, the strength of your data set. One extreme, the points appear to follow a single stream, right? So that's pretty consistent, and they appear to be going up, right? Whether it's straight, curved, bending, however you want to place it, they're all kind of joined together. Looking at scatter plots, you got strength. At the other extreme, the points appear as a vague cloud, like they're all over the place. I can't sense a pattern with that. There's no discernible trend of the data. So why would I use linear here? I can't even tell if there's a linear relationship. So no, we quantify the amount of scatter, which is what we're going to get to as well. All right. Taking a look at this. Unusual features, what we're looking for, when something that's unexpected, basically. And often the most interesting thing to see in a scatter plot is the thing you never thought you were looking for. One example of such a surprise, we call those outliers. Those are the things way out there on either side, standing away from the overall pattern of your scatter plot. You could also have clusters or subgroups. Those also raise questions. Why is there a cluster up here and then another cluster down here? What happened with our data, right? So roles for the variables. It is important to determine which of the two quantitative or quantity variables goes on the x and which one goes on the y-axis, right? This determination is made based on the roles played by the variables, so you have to know that as well. When the roles are clear, the explanatory or the predictor variable goes on the x. So when the roles are clear, right, the predictor, the explanatory, goes on the x, and the response, what you get out, goes on the y. They're just different names that you're used to seeing. Inputs, outputs, explanatory, predicted, and response, what you get out, goes on the y's, right? The roles that we choose for variables are more often how we think about them rather than about the variables themselves. Just placing a variable in the x-axis doesn't necessarily mean that it explains or predicts anything. Just because it's the predicted one doesn't mean it's going to do anything. And the variable on the y-axis may not respond to anything that you're putting there. So you got to be careful about where you place these and how you place them. Okay? Next up is correlation, and data collected from students in statistics classes included their heights in inches and their weights. And here we see a positive association, basically saying that it seems like as the height of people increase, so does their weight. And you have these outliers that tend to happen as well. All right, so for the most part it appears that way, other than that one outlier. How strong is the association between weight and height of our statistics students? If we had to put a number on the strength, we would not want it to depend on the units we used, right? A scatter plot of heights, which maybe are in centimeters, for example, and weights, which maybe they're in kilograms, for example, doesn't change the shape of the pattern, right? Just by me changing the heights, it should still be the same pattern. We talked about that with data. If you're manipulating it just by multiplying everything by something or adding something to it, right, the actual numbers themselves are still always changed. It's the mean, the median that changes. The standard deviations or the interquartile range that might change. That's what changes. So either way, even if I change these, the pattern should still be the same, whether it is in inches and height, still the same pattern, right? So that's not going to affect it at all. Since the units don't matter, why not remove them altogether, right? We could standardize both variables and write the coordinates of the points as z-scores of an x and a y, right? And here is the scatter plot of the standardized heights and weights. So if we kind of standardized them, made z-scores of them, so it really doesn't matter, right? If you took each of them and made a z-score and took a look at the heights and weights this way, this is kind of the shape of what it looks like. Still, it looks like I have an outlier there, but it's kind of all still clustered together. And note that the underlying linear pattern seems steeper in the standardized plot than in the original, right? Look at this. If you take a look at it this way, if I was just to do a rough sketch, I'm going to go with this. And this is just rough. Rough. Very, very rough. Looks like I'm going like a fraction, kind of like up 1 but over 2, or like maybe up 2 and over 3. But the point is, it seems like a fraction, right? When I look at this data, it seems like I'm going up more before I go over. Like if I was to roughly get a trend to me. It looks like it's going up more than it is over. And note that the underlying linear pattern seems steeper, like I said, and that's because we made the scales of the axis the same. They're both the same. Right now, we made them a z-score, which means it's standardized. Equal scaling gives a neutral way of drawing the scatter plot and a fairer impression of the strength and the association. So if we were to find the z-scores of the data and do it this way, it gives a better estimate of what that linear regression might actually be, right? Taking a look at these points. Some points, those in green, strengthen the impression. These are all pretty much in a line. But if you take a look at some of these other points, like the points in red, tend to weaken it, right? They're way out there. Okay, they're way out there. They tend to weaken it. It's that's not positive anymore. Like maybe it's going that way. The points, those in blue, don't really help either way. Like they're there, but they're not really doing much to change anything. They could go that way or that way. It doesn't really matter. But the point is, they just have these labeled in different colors so you can see what they're implying by this. So the correlation coefficient R gives us a numerical measurement of the strength of that linear relationship between the explanatory and the response variables. This is how you would find that. We basically said, hey, you take the z-scores, like we said before in the overview data of each of them, of the x's and the y's. You sum them all up, multiply them together, right, and then divide by the sample size minus 1. And you're never going to have to do this by hand, so I'm just showing it to you so you can see where it's coming from. And that picture and why we standardize them might have helped understand what we went over in the overview a little bit more of where this is all coming from and why it's there. For the students' heights and weights, for what we just saw, that correlation is 0.644. Well, what does this mean in terms of strength, right? Well, I'll get to that again. Well, we already hit on this before, but we'll get to that. The idea here is what we're going to hit on with correlation with these ideas. I'm going to actually stop the video here so we can kind of hopefully finish up without me being stuck in between something. So we'll hopefully finish up the Chapter 7 overview when I get back.